Okay. We are continuing our journey in characterizing 3D rotations. And spoiler alert, we are not done yet. We still have a long time to go. So in the previous video, we talked about Euler angles and how nice they are in describing a rotation using three very easy to interpret numbers that can be your generalized coordinate if you want to find equations of motion later. But today, in this video, let's talk about another thing, talking about angular velocities and how they are related to Euler angles. And from there, it's very easy to see one giant problem, not giant, an important problem with Euler angles. They are not angels. They're not Euler angels. They're only angles. All right. So, I have to write something here so we can move. Okay. So in the previous video, we saw that rotations in general are not, they are sequence dependent. So what you end up is different depending on what sequence of rotations you choose. That is true in almost always. The only exception is that if your angles, your changes are extremely small in a limit sense, so when you have infinitesimal rotations, actually that is not the case. So sequence doesn't matter that much. So for this, I have my companion again. I hope you can see it. My reference, my frame. So let's try rotating about the same sequence that we had before. Z. No, this is Z. Okay, here. Z, Y, X. So I'm going to rotate it only slightly. First a little about Z, then a little about Y, and a little about Z. So this is the sequence I get. Now let's try a different sequence. Let's start the other way. First X, then Y, then Z. So they are the same, I hope. Well, they are not actually the same, but as your angles approach zero, the difference between these two final orientations go to 0 too. So in a limiting sense, when we are looking at differentials, the difference between these two are difference between any sequences that you choose is going to be close to 0. So here, putting a note, infinitesimal, 1s or 2s, probably 2, decimal rotations are sequence independent. And that is huge because it leads the way to very easily or properly defined velocities, angular velocities, I mean. So when they are sequence independent, we can essentially work very easily with them. So remember how we defined angular velocities? It was a vector in the direction of rotation and along the axis of that rotation, right? So that was how we defined the axis of, or the vector of angular velocity. Before doing that, let's take that concept, but only at a differential level. So what I'm going to write is not very mathematically accurate, but please bear with me. So I'm going to write d of rotation. So what I mean is rotation the total rotation after a bunch of sequence of small rotations. So this is the final total rotation. What I can write is I'm working with Euler angles again. So D, and it's the same example that we had before. So let me do this. So it is the example of the same Z, Y, X rotation with sequence psi, theta, and phi. So the total rotation in a very infinitesimal sense. This one is a small rotation about K, my original K. Then I can now add them together because the order doesn't matter. I can use addition sign. I have d theta, which is about my J prime. And finally, I have some d phi about K, I'm sorry, X. This is I double prime, which is my final I. So something to note here is that the case that I'm considering is when I had started from this original sense, I have rotated to some intermediate degree or intermediate frame. So this is the K I'm writing. This is the Y that is rotated. Do you see? This is the Y prime I have here. And finally, some rotation about this Z. This is, I'm sorry, about X. This is I double prime. So something to note here that I was at this stage and my original Z was pointing upward. And these axes are actually not orthogonal to each other. And that causes a little bit of difficulty. So this is original K first or second. Let's call it second frame J, and this one is third frame I. Okay, and from here, if I want to define my angular velocity, is the rate of change of rate of rotation per time. So I'll divide everything by time, and my omega vector is going to be psi dot K plus phi dot J prime plus phi dot I double prime. And this is my angular velocity in terms of the rate of change of Euler angles. So it is angular velocity in terms of rate of change of Euler angles. But I'm writing it, remember writing it in these K, J prime, and I double prime are the sequence, are the some of them are intermediate frames until I arrive at my final body fixed frame that I should be interested in. So I'm usually not interested in these intermediate frames, especially these two. This one is equals to my final I, but K and J are something that happened along the way. I don't really know. And to make things worse, these two are not orthogonal. So actually there is some contribution from this psi dot K in the final X direction and from in other directions as well. So what I really want, not W, this is omega. What I really want is often this vector omega, same angular velocity, written in omega x about I plus omega y about j plus omega z about k. And let me make this a bit, this is big K, the original K we started with. This one is a small k. Let me write it as a little calligraphic, like this, K. So this is what we usually like to work with. So how can we do this? What we can do is write each of these intermediate unit vectors and rotate them using the known rotation matrices in terms of the final I, J, and K, if we can do this. And if you do that, what we end up with is omega x is phi dot minus psi dot sine of theta, omega y is psi dot cosine of theta sine of phi minus theta dot cosine of phi, and omega z is psi dot cosine of theta cosine of phi minus theta dot sine of phi. So if I know the rate at which I'm commanding essentially my motors attached to these joints that are rotating around, if I know those rates, phi dot, psi dot, and theta dot, I can calculate the components of angular velocity in the final frame that my body is at now. And this is usually what we will like. These omegas are omega x, omega y, and omega z are what are useful for us to do calculations. And you can also go the other way around. If you know your rate of your angular velocity, your omega x, omega y, and omega z, you can go back and calculate essentially how fast your motors are rotating. And you can do it like that. Psi dot is 1 over cosine of theta omega y sine of phi plus omega z cosine of phi. Theta dot is omega y cosine of phi minus omega z sine of phi. And finally, your phi dot is omega x plus omega y tangent of theta sine of phi plus omega z tangent theta cosine of phi. Okay. And this is the inverse. If you somehow know that your body is rotating at a certain rate, you can go back and calculate your rate of change of your Euler angles. And again, maybe I want to emphasize again, these are only for the Euler sequence ZYX. For different sequences, you have different relations. But for all of any sequence that you can think of, as long as it's valid sequence, you can find these relationships between the final body fixed velocity components and these rate of change of your Euler angles. So now maybe it's a good time to talk about the biggest issue with Euler angles. So Euler angles are not perfect, and there is one kind of important issue or limitation with them, and that is something usually called a singularity, and it is unavoidable. Doesn't matter what Euler sequence you choose, that singularity thing exists. And what is it? So for this particular example, if your angle theta, the middle one, is 90 degrees, doesn't matter which direction, something weird happens. Notice here that, and also here, when theta is 90 degrees, even if your body is just well behaving, rotating at a certain velocity that it likes, at the moment that your body goes into a certain configuration that you calculate theta to be 0, in that configuration your psi dot and phi dot will be infinite, and that is what we call singularity. The body is fine, it's only a matter of the body is just physically very nice and easy how it's rotating, not showing any sign of being anywhere in it. There's something infinite. But because we have chosen Euler angles to describe its rotation, that particular formulation of Euler angle has this limitation that at some time, for a specific combination of angles, you always have this issue of going into a situation where your rate of angular velocities, your rate of change of Euler angles just blow up to infinity. And you cannot do anything about that. Sorry to tell you. And this is something we call singularity. And kind of to see what is happening here is one thing to note here, let me write it down. In this example, when you have, I didn't finish this, let me finish it. If theta is, we have singularity, singularity. You have singularity. Psi dot and phi dot go to infinity. So that is the issue. And now I've forgotten what I wanted to say. Oh, okay. So maybe it is easier if I demonstrate this. So again, XYZ. So when the middle rotation is about Y, this is my Y. So I can rotate my Z however much, doesn't matter. So I have rotated this much. If I rotate my y 90 degrees, my new x will be in the same direction as my original z. So that is what the cause of the problem is. And both of these, if y is 90 degrees, both of these rotations kind of can share the same effect, basically. Just a little before theta is 90 degrees, they knew that the two angles phi and psi, they knew what they needed to know. As theta gets closer to 90 degrees, their effects become more and more similar, and right at 90 degrees they have identical effects in the system. And as theta passes through 90 degrees, all of a sudden maybe they have to do something that they used to do before, different from what they used to do before. And that's why we may have this sudden jump in values of psi and phi, and that's why the velocities are essentially infinity at that particular point. Let me see. Is there anything else? Oh, one last thing that maybe it's useful to mention is singularity happens if you want to go from a known rotation and find what was the angle, the Euler angle. So singularity happens in what I call inverse. So when you have a rotation and 1, 2, 1, 2, calculate Euler angles, or the rate of change of Euler angles. The other way around, going from Euler, going from Euler angles to final rotation has no issues. So if you specify your Euler angles and the rate of change of those angles, they are perfectly well defined. Your final orientation and angular velocities, you'll never run into issue in the forward direction of specifying angles. All right, so that is all I have for now about rotation. So in this video, in this maybe module, we talked about rotation matrix as a very nice and comprehensive way to fully define rotations. We looked at Euler angles, and we also looked at the angular velocities and related to the rate of change of Euler angles. And finally, we saw what's wrong with Euler angles. In the next module, we'll look at a few other ways we can describe 3D rotations, specifically something called Euler parameters. Everything here is Euler. All 3D rotation is Euler. So we look at Euler parameters. It's not in the textbook, but I might touch on quaternions. And yeah, I think that is all. There's another thing called Euler axis, but it is tightly related to Euler parameter. So, all right. That's it. That's it for now. Happy studying. I'll see you soon.